Let's try to figure out how we can get the age of the universe from Hubble's famous graph and this Hubble's law. I want to get at that by looking at two little analogies. Let's start by thinking about a dude riding a skateboard. Alright, here's a nice skateboard on some wheels. Here's a dude. Alright, and that dude's moving at a constant speed. Alright, it's going like this. Bink, bink. We'll call his speed v for velocity. Alright, now you don't see when this person left. Okay, so you actually don't know what time they started on their trip, okay? That they left their house. But you catch them a little later on, like right here. Bink, 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 bink. Skateboard, cruising. Oh, now it's got three wheels. Don't know why. Okay, there's velocity. Okay, you catch it with some speed. Alright, that's cool. And you don't know where it started back here, when it started. In fact, I'm just going to erase this thing because we don't know any of this back here. We don't know how far back his house is. We don't know anything. How long ago he left. All we know is that right now, the dude's right here. And then we see a little while later that the dude's a little further along. Okay, and he's still going the same speed on his skateboard. He's still got three wheels. Alright, he's going the same speed, and he's moved some distance. Okay, we'll call that d. Alright, and that's all we know. Let's just say that that's all we know. Okay, so we know how fast this guy's moving. It has a rate, right, like a velocity, and we know how far this guy went. Well, we could figure out the time involved with that, right? How long it took to go from here to there. Let's just check that out a second. So if I put this in regular words, it makes it a little easier, regular units. So let's just say the dude's going 10 miles per hour. Okay, and it's still going 10 miles per hour over here. And what we look and we see that this distance, just to make the numbers work out, okay, I'll say that the distance was 10 miles, even though it's a long ways. Okay, now let's check it out. Now we could just from that information, right? It's the same information. We know the speed and we know the distance. How long did it take to go from here to there? Well, the way we would do that is we'd say that your velocity is your distance divided by time. Right? Sometimes you hear this in terms of rate equals distance divided by time. So I could rearrange this, right? And my time equals my distance divided by my velocity. Now you could do this math and you get the result of 1 hour as your answer. But even just thinking about it, you probably figure it out. It's like, oh, he's going 10 miles per hour and he went 10 miles. It must have taken 1 hour, right? What I want you to see, though, is that from just a measurement of speed and distance, I was able to figure out the time that it took to get from here to there. Now let's just imagine, hypothetically, that I knew where this dude's house was. You think I could figure out how long ago this person left their house? Right? Well, I'd say, yeah, sure. I mean, if they're another 10 miles away from their house, right, then they must have left 2 hours ago. The point here is that with just speed and distance, I was able to get a measure of time. Now let's look at another situation, which is maybe a little bit closer to our universe. So let's just say here I've got a balloon that's being blown up. All right, so here's the balloon. Someone's blowing into it, blowing it up. Bing, bing. All right, and it's big right now. It's like this big. Okay? And a little while later, I'll change the color a little bit so we can see it's a little later, it's gotten bigger. Okay, so here it is a little later. Whoa! That's way bigger. Okay? And let's just say that I have here is I have a measure of how big this thing is. Bonk, bonk. All right, and perhaps I also know how big the other one is. Okay, so I know how big each of these is. Let's now say this was 1 foot across. Okay, and this is now 2 feet across. Well, maybe it's closer to 3 feet across. And more than that, now I've watched one of these guys, and I know how much it's growing. I know that it's getting bigger by let's just say 1/2 a foot per second. That's kind of a speed, right? That's how much the balloon is getting bigger. If it's getting bigger by 1/2 a foot every second, then I can figure out the time between these two instances when it was 1 foot big and 3 feet big. All right, I won't even have to do any math. What happened here? It got 2 feet bigger. It gets a half a foot bigger every second. So that means it took 1 second, 2 seconds. That's 1 foot. 1 second, 2 seconds. So 4 seconds. Okay, so the time from here to there must have been 4 seconds. Right? Because I have a speed and a size or distance. Right? And that's what Hubble's law has, a speed and a distance. So now I could take this thing backwards further still. I can say, well, at what point was this balloon 0 feet across, right? Like it wasn't blown up at all. Well, I could take that back further still, right? It was a half a second and a half a second. Let's see, or a half a foot and a half a foot. That's 2 seconds back. So I could say, well, this balloon must be 6 seconds old because I'm just playing it in reverse, right? This is exactly how Hubble's law works. Okay, Hubble's law is this graph of distance, right, and speed. Now, for any individual galaxy on here, okay, right there, that means I know how far away it is and how fast it's going. Now, let's just think that that's all I know is one galaxy, how far away it is and how fast it's going. It's important to note, though, that that distance is the distance from our galaxy to the other galaxy. So here's a way to put it. It's like, here's my imaginary balloon, right? I'll make this like, because it's exactly the same situation, I'll draw like an imaginary balloon, okay? Here's my imaginary balloon. All right? And in reality, what I'm talking about are 2 galaxies. One, this galaxy right here, right, is way over here somewhere. Galaxy, here's my awesome way to draw a galaxy, okay? And then our galaxy is this distance away, right? Here's the distance. So our galaxy's over here on the other side of the balloon, let's say. Okay, so I have a distance, and let's just say that's like, we can use whatever units you want. Now in astronomy we use like kiloparsecs, right, or megaparsecs. But it doesn't really matter. We could just say this is inches or feet or miles, whatever. Okay, so let's just say it's, we'll use the astronomer lingo, it's 10 megaparsecs away. Boom, boom. And let's just say it's going like, it has a speed, right? And we measure that speed as well. Speed we've measured using the Doppler effect. So we know that this galaxy is moving away from us at a speed of, I'm just making this up now, 1 megaparsec. We're just going to say per year, even though it's usually like millions of years. Okay, so now here's the crazy thing. We can say, how long ago was it that this galaxy and our galaxy were in the exact same place? Right? And since they were like on top of each other. Right? We know this galaxy is moving away from us, and so if we play that in reverse, they must have been closer at some point in the past, and as close as they can get is on top of each other. So how long ago were they on top of each other in the exact same place? And presumably that was when the universe began. Well, I can play this back, right? If they're 10 megaparsecs apart right now, and it's moving with a speed of 1 megaparsec each year, then it must have been 10 years ago, right, that they were on top of each other. Now here's the really crazy thing, okay? We do this measurement, and we could do that with just one galaxy, and we'd get an estimate of the age of our universe with just one galaxy. But when Hubble did this, he did it with a whole bunch of galaxies, and what he found was that they all fell on roughly a straight line. And what that means is that all of these galaxies were giving the exact same measurement, or very nearly the same measurement, for the age of our universe. In other words, it was the same amount of time, right? Since this galaxy was on top of us, and since this galaxy was on top of us, and since this galaxy, right? And what that suggests is that this is actually a very real and good measurement for the age of our universe. When we measure that, we get an enormous number, but it's a number that actually kind of makes sense with other things we know. And that is that number is roughly 13 billion years. Now, when I say that makes sense, it makes sense because we know that based on what we've seen of stars, that our sun is about 5 billion years old. Right? And so, in fact, our whole solar system is about that old. So if we found that our solar system was older than the whole universe, we'd know that something was wrong with these measurements, right? So there's a lot of things that are really consistent and that give us very strong confidence that this is a very close estimate or measurement of the age of our entire universe. Pretty cool.